In computational fluid dynamics or numerical method in general, computational scheme is very crucial, but maybe become very overwhelming if you are trying to learn the whole computational scheme. Let's say if you want to try the scheme one by one and find the characteristic and maybe the the mathematical construction, it would be like full of theories. And in this short video, I will just try to cover some important points that will be practical if you are dealing with the problem in OpenFOAM, let's say. And basically, if you just copy and paste your tutorial folder and it works perfectly, you don't have to worry much about this computational scheme. But if you are finding some errors, or maybe divergent, or maybe need a lot of time steps to finish some only simple need some lot of iterations, you can change the computational scheme. And maybe in this part I just want to show some rule of thumbs that will be used in this for practicality, and I will not discuss the detail about the mathematical background of it. So before we discuss further about the computational scheme, we must first understand what the equation behind the OpenFOAM or computational fluid dynamics in general. So we have the Navier-Stokes equations, which basically is momentum equation. And unfortunately, the momentum equation for fluid dynamics is in the form of partial differential equation, nonlinear, and sometimes, in the form of tensors and vectors. So the solution of it will be very complex. And that's why we use the numerical method to solve this. The numerical method itself sometimes divided by its term. Let's say for this term or maybe this term, let's say the gradient, or maybe the double nabla is called the Laplacian, or maybe the other term will be solved with other discretization scheme. That's why you must understand its term of this. Let's say the first term is the transient term because it consists of the time derivative. Then the second term is the convective term. It is like this, describe the whole convective flow. And this is the pressure term or gradient term because it is basically the gradient of the pressure. And the stress term, which is sometimes in the form of, or to calculate the viscosity here. And we also have the body force or external force, which is the gravity, and the other external force, let's say if we are dealing with porous region or maybe some electromagnetic field and anything like that. First, in the OpenFOAM folder, within the system folder, we will find the FV scheme and FV solution, which means the FV itself is the finite volume. So the finite volume scheme and the finite volume solution. The finite volume scheme, basically you must define some scheme that will be used to some certain term of the Navier-Stokes equation, which are the interpolation scheme, the gradient scheme, the like this nabla, and divergent Laplacian time scheme for the delta t or the time derivative term. And yeah, that's all. And for the interpolation scheme is basically to interpolate the value of from the if you have mesh or element, it will have some points which the value will be interpolated between that points. We will have some options in OpenFOAM we have like a lot of flexibility to edit this, and we have some options which are the linear, cubic, upwind, muscle, and basically the rule of thumb of the scheme is just if you have like a lower order or if you have a higher order, the process of the simulation will be faster. But if you have the faster solution, it will prone to divergent, and that's the trade-off. So you must select between speed to the solution and also the stability. And linear and cubic is basically just different in the order. And the upwind scheme, this is basically the calculation will be follows the upwind direction. So it is quite beneficial if we are solving the affective equations, which is solved from inlet to outlet or upwind. And we have also other scheme, which is the muscle or Fanlier. It is very accurate for shocks, discontinuity, and large gradient. Of course, it is not the official description of this. It is just like the best practice that has been used for some engineers. And again, this part is just like a rule of thumb, so you don't it is you can use or trial and error, use the other scheme as long as it is not error and compatible with your solver. It is also the same for the other scheme, like the divergent scheme. We have the different orders, the boundedness of the schemes, and yeah, that's all about the speed of the convergent and also the stability of the solver. You can actually refer to my book actually to see the detail of it, but yeah, you just can use the trial and error. As long as your simulation not divergent, you don't have to worry about this scheme. Gradient scheme, also the same principle, have the different order, and yeah, just about the different orders, and actually has different calculated method, but you will just find one that doesn't error or compatible. Laplacian scheme, also the same. Laplacian is like the double nabla of square. And for the time scheme or the transient scheme, we have Euler, local Euler, Kronig-Nicolson, etc., etc. And yeah, this is the rule of thumb. So the higher the order, it is more aggressive to the solution or toward the solution, but it will be prone to instability. And on the other hand, the lower the order, it is more it will be need more iterations. So for example, if we are simulating a room with steady state simulation with initiation with 30 degrees Celsius, let's say, and we will cooling with 25, maybe it will takes about 100 iteration to solve to fully resolve the temperature distribution for using higher order. Maybe if we reduce our order, it will be takes 200 or maybe 300 iterations, but it will be more stable. Yeah, that's the trade-off of the scheme selection. And then we will discuss about the solvers, but please don't be confused with the term of the solvers we use for the let's say the incompressible foam, or maybe a multiphase flow. That's also the solvers, but the solvers here means that it is like a numerical solver, or in the OpenFOAM term it's called the linear solvers. So in this linear solvers, which is inside the FE solution folder, we can select some solvers, let's say like the PCG, PBICG, and yeah, anything like that. And again, the rule of thumb of selecting the solver is just make sure that it's compatible to your solver. So it is a little bit confusing, but I mean, like compatible to your solver. Let's say for incompressible flow, it will be different solvers. For let's say for the multiphase flow and anything like that. And again, if you find it in your tutorial folder and it works perfectly, you don't have to worry about changing this solver. And it's all about stability and compatibility. And here we go. Just find the compatible one for your solvers, and OpenFOAM will help you to find the compatible solvers used in your case. Let's say if you are running this like asymmetric matrix, or maybe symmetric matrix, the OpenFOAM will suggest the choice of the solvers, so you don't have to worry about memorizing all of the solvers in the OpenFOAM library. And then one important parameter here is the under-relaxation factor, which you can also find inside the FE solution, if I'm not mistaken. So basically the under-relaxation factor is this alpha parameter which governs the stability of your solution. So it basically works the same way as the order of your scheme. Let's say if we use the higher number of URF, which is basically like typically the value of 1, it will be more aggressive towards the solution, so it will be faster to go to your solution, but sometimes it will be unstable because of the aggressiveness of the solution. On the other hand, if we use the lower value of under-relaxation factor, the number of iteration will be needed more to solve your certain solution. And to reduce this number of under-relaxation factor, it is like from 1, it is suggested that you just reduce it like a slightly just like a little bit. For let's say if you have errors, just reduce from 1 to let's say 0.95, and if you have still error, like reduce it, get to like 0.90, etc. And don't be too aggressive to reduce this number, because if the number is just too low, sometimes it will be also a numerical problem related to your solution. And yeah, it's all about the stability and the speed to the solution. Okay, and here we go. It is basically how your numerical scheme works, or your computational fluid dynamics works, is basically use some the idea of the equation of the Navier-Stokes equation has a very strong coupling between the velocity and the pressure. So let's say if we have one equation with 2 unknown, it will be very hard or even impossible to solve. That's why we have pressure velocity coupling solvers to solve it one by one. Let's say we guessing some values of pressure, velocity, and other values like the turbulent, and we solve the momentum equation to find the velocity. Then we use that velocity to solve the pressure, and then correct it and anything like that to get the whole number. And if all those parameters are converged, it will be stop, so we get the solution. If not, we will go back to the the initial case to reiterate the solvers. That's how basically the numerical method works. And of course, it is just like a very basic method or very basic algorithm. If we have other we can tweak a little bit the flowchart. Let's say if you want to make other correction term, or maybe like make it back and forth here and anything like that to make it more stable, let's say, or maybe to make it faster. And this basic idea is called the semi-implicit pressure link equation, or we know as the simple. So the other solver, like the pimple, piezo, and maybe the couple, will have a slightly different flowcharts, which you get the idea how it works generally, but you don't have to we don't have to discuss that all here. But basically this is like the summary of those solutions, or like the algorithms. First is the simple, we discussed earlier, is suitable to solve the steady state conditions. And actually simple algorithm is the most widely used in the CFD solver, so you can use it even for the transient, or maybe like multi-phase and combustion and things like that. But but if we want to have more faster solution, or like a better solvers, we use the piezo solver, which is the pressure implicit with splitting of operator. This piezo is recommended for transient simulation. So sometimes we use the in the OpenFOAM we have the different option for the simple and also the piezo, but we have also the combination of simple and piezo, which is the pimple. And we also have other option like the simplex, which is simple consistent, which is used for simple flow, but I don't think we will need this for OpenFOAM. And also couple solver to this is for steady state. But maybe the most used is the simple and also the pimple. So sometimes for the OpenFOAM template we will find like the pimple foam, simple foam, and it's just basically these solvers.